a monthly seminar series. Second Wednesday every month since 14th October 2020. 20 plus speakers presented on Cobotics. Our collaborating partners IHFC, BIRD, Cognitive Science Program, a Department of Humanities and Social Sciences. IHF Foundation for Cobotics, Technology Innovation Hub of IIT Delhi, a national mission on interdisciplinary cyber-physical systems by DST, Department of Science and Technology, Government of India in March 2020. A Section 8 company, IHF Foundation for Cobotics, IHFC, was incorporated on June 13, 2020. About IHFC. Advances in sensing, computation, and autonomy are enabling robots and autonomous systems to enter real-world domains such as manufacturing, defense, medical, agriculture, etc., where machines must work alongside and interact with humans. We are entering an era of manned and unmanned teaming where humans and robotic systems must work together towards common goals. The four verticals of IHFC: medical, agriculture, industry, and defense. Our goals: human-robot collaboration for enhancing human capabilities, reducing risk and improving productivity. Our objectives: research on novel technology areas of robotics and automation science, development of products for benefit of society, inculcation of startups, and promoting entrepreneurship in India. Our CQ: concept, collaborate, commercialize. From research to product. Grand projects of IHFC: medical simulator, human-robot interaction control, rehabilitation robotics, drone applications, healthcare robotics, human-robot interaction intelligence, intelligent sensing and secure communication, and Industry 4.0. BIRD, a center of excellence at IIT Delhi. About BIRD: biologically inspired robots and drones. The Center of Excellence on BIRD, biologically inspired robots and drones at IIT Delhi is an evolution from its humble research activities, which began a few decades ago by its faculty drawn from the Department of Mechanical, Electrical, and Computer Science Engineering. BIRD has 10 plus projects, industrial and academic, 27 plus members including faculty, students and technical staff across various departments of IIT Delhi, 150 plus publications in international and national conferences and journals, 9 years of experience. Cognitive Science Program, a Department of Humanities and Social Sciences at IIT Delhi. Cognitive Science Group at IIT Delhi is to create a knowledge pool that can address relevant problems under the ambit of human cognition both for India and the world at large. It helps students acquire a strong background in theoretical frameworks and empirical approaches of one or more areas of cognitive science. Cognitive science is an emerging new field of study that endeavors to study the mind from multiple perspectives and disciplines by combining ideas, principles, and methods from psychology, linguistics, philosophy, computer science, and neuroscience. This knowledge is applied for developing a better understanding of how our minds, brains work while creating better products, tools, services, policies. CoboTalks, leading the way in the human-robot collaboration space. IHFC.
So now over to Professor Saha to introduce our speaker.
Okay, so good evening to all and good morning to Xavier. So it is a pleasure to introduce Xavier Cyrill, our Dr. Xavier Cyrill. We have been friends way back in 1987, I think, if I remember correctly. And he did a PhD at McGill University, and later on he worked with CAE, who is the biggest probably the simulation company in the world, and he has a long experience in the area of simulator. Without spending too much time, I would rather like to hear him, or all of us would like to hear him sharing his experiences and how we can benefit for our IHFC and our ambition simulation project. Thank you, Xavier, for agreeing, and hand over to you.
Thank you, Professor Saha. Thank you to all the audience. Good evening to everybody. Namaste. It is morning here. I know that it is your evening. Hopefully the next 45 minutes of your evening is not wasted. Hopefully you'll have some useful information from my talk and you benefit from it. So I'm going to cut my video now. I'm going to start sharing my screen. I would request everybody to mute their mics, and I understand there's a Q&A at the end, so if you have questions, we can entertain questions and discussion at the end. So can you see the presentation now?
Not yet, so.
Oh, okay.
It came and gone.
Yep.
Now?
Yes.
All right.
Yeah, it is.
Thank you. Good evening. The title of my presentation is Simulation Assisted Product Lifecycle, as it is shown here. The picture you're looking at is the International Space Station that is orbiting around the Earth at 500 kilometers orbit. And the relevance, why I chose this picture for my talk, is because I finished my PhD in space robotics modeling, simulation, and control. And I started my career at CAE in 1989 to work on the space station program. And at that time in 89, the space station was not built. In fact, it was only a concept, a lot of paperwork that was done. In fact, there was a joke that was being made at that 1989 that if we had stacked up all the paper we created, we could reach the orbit. At that time, simulation played a significant role in the conceptualization, design, and development of the Canadian robotic arm. And with that preamble, I'd like to make this talk and presentation. Bit of a background. Simulation has played a vital role in product training for decades. And in fact, as Professor Saha mentioned, I started my career at CAE. We were certifying pilots in a simulator. In fact, for over 4 decades, many fields like nuclear, aviation, space, operators were certified 100% inside a simulator. So we all know that simulation was used for training for years. However, in the 80s, simulation also started becoming more popular in the product design. Now, I want to point out, when I talk about simulation, I'm not talking about simulation of a subsystem or simulation of fluid dynamics or simulation of a finite element. I'm talking about full system simulation. And when I'm talking about simulation, we are exclusively talking about real-time simulation. And in most of the cases, we are talking about high fidelity functional simulation. And that is what the differentiator between everybody who talks about simulation versus when I talk about simulation. With the advent of powerful computers and visualization technologies, simulations are becoming even more popular in product engineering and maintenance. One of the challenges when I started my career in CAE was computer power wasn't there. And graphics technology didn't even exist. Commercial graphic technology didn't even exist. We had to solve a 100 by 100 matrix in a supercomputer in 1989. Today, the same model and real-time simulation I can run it on my laptop. So you can see the evolution of computing technology. Graphics did not exist then. We had to build our specialized graphics boards. Today, I can buy a general purpose graphics board on a laptop and I can run fancy visualization. So that's the cutting edge. I have been privileged to working for several companies, starting with CAE and then L3 and now L3 Harris Technologies, where cutting edge technologies in simulation control and visualization have been developed and deployed. I have contextualized my 32 years of experience in this presentation titled Simulation Assisted Product Lifecycle. It gives a nice a bridge to all that I've done. Hope this presentation will stimulate the discussion in the context of Cobotics. I just saw the vision of Cobotics, and I think that it has a lot of relevance of my talk in the Cobotics vision. Okay, so how can simulation assist in product lifecycle, and how and in what forms? This is not as popular as it should be. Simulation should be considered even before you decide to build a product. You want to visualize the product concept and use it to buy in stakeholders before budgets, large budgets for product development are done. Now, granted, when you start a simulation using just concept, you are only using simulation in a generic sense and with assumed data. But that is sufficient enough to get the buy-in from stakeholders. And once you have secured the budgets for our product development, one of the fundamental and most important activity you undertake is called requirements definition and requirements analysis. I cannot overemphasize this phase of the product because this will save you a lot of headache when you deploy a product. If you iron out and visualize all the requirements that you want in the product, you have much easier time at the time of the acceptance of the product to the stakeholders. And this is also called systems engineering. And simulation can play a great role in validating requirements and analyzing requirements. Again, as I said before, at this point, you don't have the product data. You are only working with assumed data and generic component functionality. The next phase is once you have done the requirements analysis, you have signed off with your customers or your stakeholders the requirements, you start the design and development. And this is very popular. Many people use engineering simulators, but they use part task engineering simulators. What I'm suggesting here is using a full system engineering simulator to verify and validate. And throughout this presentation, you will see how we have been successful in various domains of using engineering simulators. Once you have done the design, verified and validated and demonstrated to your customer using an engineering simulator, you get the sign off at preliminary design review or critical design review. Now you move on to the product integration and testing phase. Now, this again, we have successfully used simulators to do validation at the subsystem level. Now that your simulation, if it is in functional blocks, if one of the function you actually have the real hardware, you will plug and play that real hardware into the simulator called the hardware in the loop simulation. Now, as you can see, the simulation is progressively getting better and better. It's increasing in its fidelity. Now, throughout this life cycle, the simulator, not only you're building the product, the simulator is also getting mature. Now, once you've finished the integration and test, you are ready to do the training of the operators in a full mission simulator. And once you have trained the operators, then you are deploying the system. And while you're deploying the system, you need to train the maintainers in a high fidelity simulator. And once the system is operational, and then you can continuously improve the simulator if the system is being updated to reflect the simulator as an as-built simulator. Now, you may already have heard terms like digital twin. Digital twin is nothing other than an as-built simulator. Now, all these are great. What I'm advocating is using simulation throughout the product life cycle from concept to maintenance. Now, in order to do that, you need a versatile simulation development environment. Not only that, you need to have a robust configuration management mechanism because you're having several versions of the simulators at various levels of maturity, and you have data at different levels of maturity. They all need to be properly configuration controlled. With that kind of a tool in your hand, now you're ready to use simulation in a product life cycle. So the first thing we did in my company in the 80s, we quickly realized building complex simulators like the nuclear power plant, which is so complex because it's got the nuclear physics, it's got fluid dynamics, it's got control systems, it is got radiation effects. So all those models have to be developed. So we had to deploy large teams of engineers to code and test various systems. One of the things we realized is engineers, we were hiring chemical engineers, mechanical engineers, electrical engineers, electronics engineers. They finish their engineering, they come to industry, and they start syntax checking Fortran or C, C++. All their engineering knowledge is sort of put in the back shelf. They are doing syntax checking. So we realized, what if we developed a graphical based simulation environment where engineers do not have to do coding and testing, do not have to look at codes, rather they look at systems, they do more systems engineering and utilize their knowledge effectively. And that's when we decided to develop this product called ORCID. The pictorial that you see in front of you is the ORCID development environment. It has the It has the development environment, it has the deployment environment, it has the environment to incorporate control systems, it has the environment to incorporate hardware in the to emulate hardware, so you can do hardware in the loop simulation as well as prototyping human machine interfaces. Now, this subject alone, the simulation development environment, this slide you're looking at, it's almost a 2-hour long presentation, so I don't have the time for that. So I'm just going to show you a small snippet of the intuitive drag and drop connect model development environment. So what you're looking at right now on the video is a drag and drop simulation environment. In this case, a mechanical engineering is dragging and dropping objects that is required for building her system. She understands mechanical engineering, she understands control systems, she understands process. She doesn't have to worry about the code, because as she drags and drops the objects, the simulation of the objects and the simulation of its interfaces are all behind the scenes. If she ever wants to look at it, she can, but at this time it's not required because these are validated objects. Now, this environment, another benefit of such an environment is, as you can see, simulation development becomes very rapid. Number two, the second biggest advantage is chemical engineers, mechanical engineers, electrical engineers, all of them can do their models in the same environment. You can do electrical diagrams, hydraulics networks, control networks, process networks, all in a single environment, all seamlessly working together. The third benefit is that they can all collaborate in the same environment. There is a strict check-in, check-out mechanism. Therefore, nobody is stepping on anybody else's toes. So everything works seamlessly. And many developers can work in a very strict configuration control environment. The modeling environment is the same environment that you see during your simulation, because the same schematics comes to life. So with that simulation environment, now we are ready to take the challenge of using simulations for product development. Now, transforming knowledge into concepts. Once you have a validated set of libraries, you are ready to use that knowledge to conceptualize. As I said, one should always consider simulations in early stages of a product development lifecycle to conceptualize what they are trying to build and what they are trying to achieve, what performance they would like to do. So the what if analysis is possible in such a powerful drag and drop graphical environment. At this stage, we, again, like I said before, we are working with generic components and assumed data. These generic components will become more specific as you go along developing the simulator in parallel with the product lifecycle. What you're looking at on the pictorial here is a satellite simulation environment. This was one of my first projects when I joined CAE. And for reference, again, this is a large subject. It is another hour-long talk about how satellite simulation can be done in this environment. I have put the reference of the paper that I published in 1998. And throughout my presentation, wherever I can provide a reference, I'll provide the reference of the paper. So you can, at leisure, read more in depth of what I have discussed here. Again, like I said, I want to point out here is this kind of simulation at the early stages of a program can be also used for cost-benefit analysis prior to committing full product lifecycle budgets. I know that the United States DoD uses simulation in simulation-based acquisition even before they secure budgets. And I don't know where else, but it should become more popular. So like I said before, I started my career at CAE to work on the International Space Station program, to work on the robotics simulation, since I had just completed my PhD from McGill in that field. The very first thing we undertook was building a simulator for the design validation of the robot design, the kinematics, the dynamics, and validating the control system. And the same engineering simulation core was later used in building a full mission robotic simulator for mission planning and operator training. We developed and delivered the simulator in 1997. For the last 24 years, we are maintaining the simulator, the Canadian Space Agency. And like I said before, the simulator is progressively improving as we get more data from the space station to reflect the maturity of the station, as well as the data associated with that. So far, we have trained over 100 international astronauts from all over the world, Russian, Japanese, European, Canadian, and American. Again, I have provided the reference to the paper that gives you in much more detail the system architecture, the functionality, the benefits of this simulator. The video you are looking at now is the one of the many robotic operations that were done on the station. I don't know if everybody knows, this entire robotic, space station was built using robots. And it is continually building more and more, adding modules, replacing modules. What you're looking at is the visualization from the robotic simulator. This operation, that is this 2-minute video, is really a more than 2 hours of operation. This is a man-in-the-loop operation. Here, the astronaut is manipulating the robotic arm totally blind. He has no view of what's going on outside the station. He's inside a cupola, and the only thing he gets to see is 3 small screens, like 10-inch screens. And on those screens, he's looking at the CCD camera views. One of the biggest challenges we had building this simulator was providing the astronaut the fidelity of the dynamics as well as the visuals, because the astronaut is completely relying on the visuals to do the manipulation because he has no depth perception. He's using 3 flat screens to determine the depth. And in order to determine the depth, he uses shadows as a cue. And in 1997, when we delivered the simulator, we did not have the powerful graphics technology that we have today. We had to build specialized hardware for graphics displays. Today, we have ported all of that to general purpose computers and general purpose graphics hardware. In fact, this simulator can run on a laptop today. This was one of the most successful projects we have ever done, and this is considered only one of its kind in the world, stationed in Canada. The simulator, and international astronauts have to travel to Canada to do the training. It also gave us a lot of PR. A lot of other domain people came and looked at our simulator, and one of the domain people that looked at the simulator were most interested were surgeons. And that led to our next project. Canadian surgeons who saw the robotic simulator approached us to build an endoscopic surgical simulator for training students. Typically, surgical students train on cadavers. These are pigs. cadavers were becoming scarce, and the students were not able to do a lot of practice. That's why the surgeons looked at our simulator and said, hey, what if we guys build a simulator that has the fidelity and the feel of a real endoscopic instruments, and we could do the training inside a simulator. Additionally, what the surgeons noticed is that on the astronaut training simulator, we were recording everything that the trainee is doing. We were doing performance assessment. We can score them where they did well, where they did not do well. Whereas in surgery, the surgeons are trained with no performance management. In fact, a surgical student looks over the senior surgeon, and then one day, voila, he's ready to do surgery. This is a scary thought. So like flight simulators, like the robotic simulator on station, I think the medical industry is heading towards performance-based training. And in order to do performance-based training, you need high fidelity, reliable, realistic simulators. And that's when we started developing the surgical simulator. It has high fidelity physiological models and tissue simulation. Again, I'm providing the reference at the bottom. The video you're going to look at is a thoracoscopic lobectomy procedure. What is that? Thoracoscopic lobectomy procedure is a procedure done at the chest cavity area to endoscopically enter and isolate a piece of the lung that has been malformed and cut it out and remove that lung. I understand lung is like a sponge and it'll grow back. Apparently, babies are born with malformed lungs, and this is a very common procedure in less than a month-old babies. So what you're looking at is a pediatric thoracoscopic lobectomy procedure. We built a simulator. Everything is simulated and graphically represented, but the instruments are real instruments, and we have provided a full haptic feedback so you can have feel of the tissue, tool tissue interactions. Our engineers were not doctors, but some of our engineers were so interested, they studied physiology and they learned how to do physiology modeling. They went and attended these surgical procedures on cadavers, collected relevant data, talked to the surgeons and asked them how they feel when they cut the artery, how they feel when they touch the lung. And so we modeled all of that into the simulator. One thing I want to point out, which is of relevance for this talk as well as for Cobotics, is we did not reinvent the wheel here. We actually built the simulator on top of an open source called SOFA. And we enhanced SOFA, obviously. SOFA did not have all the functionality. We enhanced it. And that's why we could build the simulator in 2 years. Otherwise, it would have taken many years. And so the message here is, do not reinvent the wheel. When possible, use open source. There are many other benefits of this simulator. We have not fully explored it. One benefit we see is that if you want to try new surgical instruments, you can try it on the simulator before you actually deploy it in an operating theater. Okay, so the next project, this is another important project I have been involved in. It is one of the world's leading edge simulators stationed in the UK. In the 90s, the United Kingdom Royal Navy came to us and asked us to build a submarine simulator to train submariners. This is a nuclear submarine. So we built this simulator for it is a futuristic simulator because the man-machine interface of this simulator is completely different from the old days simulators where everything is done using hardwired buttons and switches. This is all glass panel based. It's like a flight simulator in other words. This simulator is operational since 2007. Several submariners have trained on this simulator. One key point I want to point out is that this simulator, when we delivered this simulator, we used the engineering models and enhanced it in this training simulator. And once the submarine was deployed, one of the things we found design flaws on the hydraulics network on this training simulator, because this training simulator had the full mission simulation, whereas the engineering simulator was only a part task simulation. So there you go, the benefit of doing end-to-end full mission simulator. We were able to identify a design flaw, and that was subsequently brought back into this real system and modified. And there's one of the benefits of a full mission simulator other than just training. Like I said, this is the only one that I know of a 6 degree of freedom submarine simulator. There are many submarine simulators in the world. They tend to be 2 and 3 degrees. And this is the only one I know of that's 6 degrees of freedom. For over 4 decades, nuclear plant operators have been training on full mission trainers to get certified. In fact, a nuclear power plant operator is certified to operate a plant inside our simulators. In the recent years, these full mission simulators are also gaining popularity in plant design, especially now, as you may have heard, the world is going towards something called SMR, Small Modular Reactor. And this market, in order to test out, there's more than 50 different designs that are being tested throughout the world, and simulators are playing a big role in plant design. The video that you're going to see in front of you is the virtual simulation of a nuclear plant. Now, this is an offshoot product that we developed in the last 10 years. And now with the pandemic, we are finding that this has come in very handy to provide remote training to operators before they are ready to go to the real simulator training center. And such a simulator can give you the ability to familiarize with the systems, even test out some operating procedures, not necessarily everything, because you don't have the replica control panels here. And you can do severe accident simulations, do virtual radiation training. Again, like I said before, for the medical simulator, this simulator and all other our simulators that are virtually delivered are managed within a learning management system to track the students. And again, I want to point out this learning management system we did not build from ground up. We used an open source and enhanced it to develop a learning management system and track the students. The next subject is shipboard automation and training. Now, this is the big business of the company. We have been developing automation systems for navies around the world. In fact, Indian Navy has our automation system. What we realized is our Navy customers were approaching us and asking us, typically they train their maintainers, shipboard equipment maintainers, on real equipment. In order to build a trainer using real hardware, it is an expensive proposition, depending on the equipment. And so they realized that simulation technology is so far advanced and virtualization is becoming popular. They came to us and asked for an alternative to expensive hardware-based training. And this is when we developed this technology that you're going to see in the video. This is a virtual maintenance trainer. What you're looking at here is a ship operator is first isolating a fault on the system. He's sitting in front of a control screen and seeing what has gone wrong on the control screen. Then typically he will isolate where that problem is, and he'll go down to the equipment to see what failed on that equipment. So what you're looking at is a 3D virtual equipment. So here he can walk around, he can open the doors, he can virtually do exactly what he can do on the real equipment. He can pull up spares, he can pull up instruments, and he's right now isolated the problem onto a control module, and he wants to replace it. And once he's replaced that, he wants to verify that he has actually fixed the fault. Now he's going to put the replaced parts, turn on the equipment, and he's going to go back to his control station to see if that equipment fault has been resolved. And as you can see, the magentas have gone and the fault has been fixed. This kind of a training, what we are realizing, is also very useful in providing remote and just-in-time training. Imagine if you had a system like this on board the ship, and let's say the maintainer has forgotten, or he's never been exposed to how to maintain that equipment. He can do just in time. He can open up the laptop and do this kind of a training before he goes and touches the real equipment. And that's one of the benefits of doing everything virtually. Now, you may all have heard, virtual reality is so popular. Gaming world is everywhere. Your kids are playing in different gaming environments. Immersion is becoming really popular in all kinds of industry, gaming, entertainment. It's also slowly entering the engineering and development and training marketplace. What you're looking at in front of you is one of the many immersive environments you will see in the marketplace. What you're looking at is a 280-degree field of view immersive environment where you do not need to wear headsets. You are free. You can move your head around without the constraints of a headset. Many people can be in the same environment. This, what you're looking at, can house about up to 15 people inside that. This kind of an environment allows collaboration in a simulated immersive way for doing all kinds of stuff like design concept validation, workflow assessment, familiarization with systems that you don't have vantage point views because it's hard in the real world. You cannot go in there, and you can train in a collaborative sense. It's a very short video, and just to give you an idea what this is all about. So you can virtually visualize any system. Here you are looking at a shipboard system. You can walk around the ship. You can go touch any equipment. You can operate any equipment. You can move equipment if you're in the design environment. What you're looking at here is the nuclear plant. We are about to deliver the world's first virtual nuclear plant to United Arab Emirates for the Baraka nuclear plant. where our customers will use this virtual trainer for all kinds of training, systems training, procedural training, and most importantly, radiation leak training. In fact, in this trainer, we have also simulated avatars that people can wear. We will teach them how to use radiation equipment, use Geiger counters to monitor the radiation environment, and find your way to the safe places and identify leaks and things like that. This technology also has the potential for applications beyond what we are doing. In fact, there is no limit to it. In fact, the more we look at this technology, we are realizing we could use it for this and that we have never in the past realized. Visualization is a powerful technique to make a mental map of what you're looking at and what you need to do. And my final thoughts, in the current environment of cheaply available computing and mature simulation technology, simulation can be used to conceive, design, build, test, train, and operate. As I demonstrated in my presentation, I did not give justice to each subject in depth, but at least you got a glimpse of it. And we have shown that we have been successful in various domains in various phases of simulation. What is important is that before you commit, if you are going after a large project with lots of budget requirement, simulation can be an excellent tool to get the buy-in from stakeholders. What is important is also to choose the right simulation environment that will facilitate collaboration and facilitate configuration control and configuration management. Otherwise, it'll become very messy. Like I said before, do not reinvent the wheel. Try and explore open source where applicable, where available. Obviously, it's not available everywhere, but try and use open source, and the open source market is getting bigger and bigger. Virtual reality, as I demonstrated, is a viable technology today to be exploited throughout product lifecycle, and immersive technologies is becoming cost effective. In fact, I only showed immersive technology without headset, but there are cheaper immersive technology with headset. In fact, we used headset-based immersive technology for our medical simulator. And final thought is, please spend more time during your requirements phase to avoid pitfalls in later phases. Because once you have your requirements well defined, and use simulation to visualize your requirement, because normally people do requirements on paper with words like shall, will, and may, and should. What I say as a shall and what you interpret as a shall could be different, and that is what comes to bite you at the end of the project. If you had visualized it, simulated it, you narrow that gap of expectation versus delivery. And with that final thought, I will ask the audience if they have any questions. Thank you.
Thank you, Xavier, for very interesting and eye-opening lecture. And I would let Udayan to control the question from the audience.
Yes, thank you, Professor Shah. So I would now request the persons from audience who are having question to raise their hand using the raised button. We will call them sequentially. Yes, the floor is open. In case someone is not able to raise their hand, they can unmute themselves and put up their question. Okay. Yes.
Yeah,
Please
maybe I
start.
begin to break the ice. Many times, Xavier, we encounter this question from the customers. I mean, customer means as a faculty when I work with some industry consulting project or any project. No? When we talk about the simulation part, no? So sometimes they show hesitancy in terms of thinking their project will get delayed, or no, sometimes the realistic things may not be possible. So how do you suggest that aspect to be taken care?
Okay, so you are absolutely right, Subir, and I have seen that all the time. Simulation always has been an afterthought, and that's because they don't set aside budget for simulations, because not a lot of people have really faith in simulation, but people who have been in the industry can vouch for it, and I can show you. Millions and billions of dollars of products are being built today with simulations. So the only suggestion I would make is that you do not, at least for your first attempt, you do not want to tie in simulation as a roadblock for your product development. So give the flexibility to the product development team and say, look, we are not going to come and stop you because our simulation is results are not ready. Let us at least experimentally try this. Have a two parallel path. You have product development and simulation development. And if the simulation is ready enough, you go look at it and you come back at it. No matter what, whether it is giving good result, bad result or not, you go back to your product life cycle. Do not interrupt it. Build confidence in your simulation. Number two, let's say in Cobotics is all about robots. First, maybe don't even tie it to a project, but say we want to build a library of robotic devices simulation, a separate, a little small project. And then come in and say, look, I have all these validated objects and I've done the simulations. Now, the next time you build a robot, I will show you the simulation. And it should be very rapid. They don't have to wait for you. The problem is until you demonstrate something, nobody's going to buy into it, right? You can't talk about simulation. You have to show simulation.
Oh, thank you.
So, are there any other questions? So I guess we have a questions from the chat from Sagar. He says, what language is most effective when it comes to building efficient simulation slash graphics in your experience? What he sees is C++ is very popular. Are there any other languages?
Okay, good, very good question. Very hard to answer. Okay. When we started this in the 1980s, everything was Fortran. Engineers only knew Fortran, right? And Fortran is still an amazing language that's why it's called formula translation. If you have a matrix inversion, if you are solving a simultaneous equation to translate into code, Fortran was the best. So we built those many years ago and we are still maintaining that in Fortran. However, Fortran compilers are becoming very, very difficult to find, right? So wherever we could port it to C, C++, we did it. When we could not, we stayed with Fortran. Now, the most popular language is C++ and C#. It depends. If you're doing modeling of physical systems, it's better C, C++. If you are doing HMI, human machine interface graphics, is C# and the more modern languages. Any database polling interaction between database and the client server, there's so many new technology. You got this, JavaScripts, and now the new one is called React, and um, there's so many, I can't even keep up with it. So it depends on the domain. For math translation, C++. For HMI, C#, and for any other computer interaction between database queries, user interface interaction with the simulator, it's React, JavaScripts, and things like that.
Okay, so Venkat sir, you can go ahead.
Good evening, sir. So I have a question like how close, say, the confidence level of a simulation and the real implementation should we look at in a in a project or so?
Good, very, very good question. Depends on the outcome you're looking for. If the simulation you're using for concept design, fidelity should not be a big issue. If you're using it for design, yes, fidelity plays an important issue. If you're going for training, you want a good fidelity that you don't provide negative feedback. How do you build confidence? You need validation. We spent years validating. For example, our submarine dynamics and robot dynamics was validated. Several ways we have validated. We validated against another model. For example, the robot dynamics model. Our dynamics model was compared to results of another dynamics model. That's not good enough. Then our dynamics model was compared to experiments, ground-based experiments. Number 2, that's still not good enough. Now the third level, the final one, is when we got onboard data back, we were validating that. So it is validation is a progressive exercise. You can't do it on one day and say, I'm done it. You'll never do it. It's impossible because there has to be progressive validation. You build confidence. And that's where you need to have your stakeholders buy into it from the beginning and need to be part of the equation. And so validation is a very important exercise, a good question, and you need to have a validation plan. How do you validate? Analytical validation, experimental validation, real data validation. There's 3 levels of validation. And for training simulators, you do need systems that are validated at least to the experimental level. And because on the training simulators, certain aspects are more important than the others. The human-machine interaction is more important than whether the dynamics, second harmonics is being included or not. That's not very important. So, but when you're doing control system validation, you do need the dynamics to have all the modes in there because you are controlling it. So.
Thank you, sir. Thank you for the clarification.
Mr. Arif Sohail, you can go ahead.
Good evening, sir. I have a question. If a student is just starting his journey in the direction of simulators and robotic simulation, do you have some good resources or books that can be referred to and some tools where initial training can be done so that they can venture into this field?
Oh, I'm not the expert in this field. Professor Shah is the authority in robotics. He's written books too. I'm sure he can provide you the robotic simulation. I am a little bit rusty because when I did robotics, I was doing robotics in the 90s, and after that I moved to nuclear and marine. So I'm a little bit rusty on the robotic simulation books, but the books that I used are still good today. But Professor Shah would be the best to provide you the reference list. As far as this generic simulation out there, I don't know of any that is available in the market, but I'm sure they are there. But this is the problem. You see, everybody reinvents their wheel. Nobody will look at start from somewhere. If you go to one research institute, they're using one robotics dynamics model, and another will use another one. And I've seen that throughout my life. Whether if you go to NASA is using their own model, and Canada is using their own model. Japan is using their own model. What we, at least we were able to do for the training, we said, no, we're going to use one model, and that is our simulator in Canada, because that way we don't have negative training. I don't know if I've answered your question.
You guys help him, no problem.
Yeah, okay.
Okay, so we can move to Rajiv, sir.
Yeah, Xavier sir, I joined in a bit late. Sorry for that. So there was a model you showed about virtual reality. There was a dome. So can you please explain what are the technologies in the graphics visualization used in it?
Yeah, it's again well-known Unity.
Okay, Unity in C#, right?
Yeah, exactly. Unity, and we have also used CryEngine, Unity, and there's a third one. So yeah, they're all, Unity is on open source.
Okay. Actually, I don't know whether Professor Saha had mentioned, we also have a software called Robo Analyzer. So that is developed using C# and OpenGL, so which has a bit of graphics, but the challenge we faced is obviously OpenGL is not very developer friendly.
No, try going to Unity.
Okay, and how
Because
about you have
my
any?
suggestion is everybody is going to Unity.
Okay, sir. And how about iShot? Have you been using it? DevDept, an Italian company, has an iShot. It's an SDK developed using C#.
Okay, no, I have not. No.
Okay, maybe whenever you have time, you may please explore that also. That also has good, but it's a paid one though. Okay, thank you, sir.
Thank you, Rajiv, sir. So finally, we have two questions, small one from my side and one from Rahul. So Rahul says that how do you account for the delay of communication between operator to arm during simulation? And mine one is also somewhat related to that. Like, how do you take into account the real-time effects while you are simulating?
Okay, so if I understand correctly, the first question is the delay between the ground and the space station.
Yes, exactly, sir. That.
Okay, the robotic operation, most of the robotic operation are done in space. Inside, the robotic operator is sitting inside the station, inside a module, the lab module. So there's no delay. But any ground operations, any ground manipulation are done semi-autonomously. So they send a command and the robot autonomously does a small task and comes back with the results.
Okay.
Number 3, if we need to model the time delay, in fact, this is an interesting exercise. I did another project controlling a robot using a satellite link. That is, I am sitting here and the robot is in New Delhi. And I want to control from here the robot in New Delhi through a satellite link. I send a command from here and the command is received by the robot and I get a visual display back from the robot and I see it. There's a huge time delay. And as you know, in space, it's a 4-second delay to the low Earth orbit. We did model delays, but that doesn't, you have to still rely on something called a predictive display. That is, you send your command to a robot's simulator in your place and have the 4-second delay modeled in there and get the visual back and see, oh, okay, this is where it will end up. So you have already predicted where the robot would be.
Yes.
So you do a predictive corrective model. We demonstrated that about 20 years ago, that technology. So yes, you can model delays, but in most of the case, by the way, Canada is ready to Canada has just signed on to build the moon robotic arm. They're going to put a space station around the moon, and they're going to have an arm on that. For that, they are clearly looking at autonomy on robotic operations, not man in the loop.
Okay. Thank you, sir.
What was the second question?
Yeah, the real-time effects. I think you answered it in your first part.
Okay, so that's a good question. I could talk for an hour on the real-time effects. In fact, that was the thing that I did when I joined. I had to model a 100 by 100 equation because we were modeling all the flexible dynamics of the arm. And in order to do that in real time, we could not find a computer. We had to parallel process that in a supercomputer. Like I said earlier in my talk, now that same model is running on my laptop. That powerful our computers are today. So real-time modeling, we were iterating the equations every millisecond. We had to get, so that was a big challenge. That was a challenge of the computer science and computational dynamics in those days. But all that is solved now. We have technologies, both hardware technologies as well as software technologies to solve all that problem in real time.
Okay. Thank you, sir. So do we have further questions? Let me just.
Actually, maybe it's a time to maybe close within a minute or so.
Yes. So maybe Professor Saha can give a vote of thanks.
Yeah.
Long term.
So thank you, Xavier. It's very nostalgic to see you talking, for last 1 hour and so nicely, even though you are in the industry, but your patience and the way you're explaining, it's like another professor talking actually, right? And I'm sure you will be in touch and you will be educating us with your vast experiences. And so thank you very much, and let us try to recreate such an environment again and again. And I'm sure, as you see the enthusiasm amongst our audiences who are not only from Delhi, they're from various places. So thank you again, and all the best, and have a good day.
Thank you. Thank you to everyone.